Hello everyone, I am Siddharth Nayak and I'll be presenting a paper on improving object detection with reinforcement learning. The performance of a trained object detection network depends a lot on the image quality. Generally, images are pre-processed before feeding them into neural networks, and domain knowledge about the image dataset is used to choose the pre-processing techniques. We present an algorithm called ObjectRL to choose the amount of a particular pre-processing to be applied to improve the performance of a pre-trained object detection network. ObjectRL is a reinforcement learning agent trained with rewards according to the improvement obtained in object detection. One of the key things to note is that an image which looks good to a human eye may not necessarily be the optimal one for detecting objects. So the pipeline for the algorithm goes something like this. We have a data set of images which can be any standard data set of images like CFAR or Pascal VOC. We follow the standard process of dividing the data set into training and testing sets. Now the images from the training set are digitally distorted to simulate bad images and get a greater variety in the images seen by the reinforcement learning agent. This distorted image is given to the agent. The agent takes action on the image and hence is digitally transformed. This agent obtained image is fed into the object detector where we get the F1 score and the intersection over union for the bounding boxes detected. We evaluate the reward with it and then give this reward to the agent. Although this process can be repeated n times on one input image, we set the value of n to be equal to 1 for training stability. This is because in the initial episodes of training where the agent is exploring, it takes random actions which distorts the image so much that nothing can be detected in it, and hence the rewards are small and it never learns anything. The digital transformations we work with is brightness, color, and contrast of the image. One of the key motivations of ObjectRL is to be able to use it to capture images in real time by changing camera parameters like shutter speed, voltage gains, etc. to improve object detection. Although we work with digital transformation, ObjectRL can be extended to choose camera parameters to capture the images by using the image formation model proposed by Hasanoff et al. We use these formulae for digital transformation. For the digital distortion of images, we choose the value of alpha according to the distortion scale as explained in the next slide. For the agent transformation, it can choose a value of alpha from 0 to 2. For the experiments, we use 2 degrees of distortion. The first one being the full scale distortion, where the value of alpha ranges from 0 to 2. The second type of degree of distortion is the minor scale distortion. Here, the value of alpha can range from 0.5 to 1.8. This constraint limits the images to not have distortions which cannot be reverted back with the action space the agent has access to. In this slide, we show the effect of distortion on the images. The first 2 rows are for brightness, the second 2 rows are for color, and the last 2 rows are for contrast. So here the value of alpha changes from 0 to 2, similarly for color and contrast. We define the reward system used for the training the RL agent. First of all, we define dt of x, which is a convex combination of the intersection over union of all the objects detected in the image and the F1 score for the detected objects. Then we evaluate do of t, dd of t, and ds of t, which is dt of x evaluated on the original input image, the distorted image, and the agent obtained image respectively. Then we calculate beta t, which is 2ds of t minus do of t minus d dt. So beta t will be positive only if the agent obtained image performs better than the original image as well as the distorted image. So we give a reward of +1 if beta t is greater than minus epsilon, where epsilon is a small positive number, and -1 otherwise. Motivation for ObjectRL. As mentioned before, the main motivation for ObjectRL is to extend it to capture images in real time by choosing appropriate camera parameters. This can be used in real-time detection scenarios where the lighting conditions and subject speeds can change over time. In these cases, single operation mode on cameras will not work well. Also, in these cases, it would not be possible to capture images obtained with all combinations of camera parameters, along with manually annotating them with bounding boxes. Also, due to lack of these annotated images, we cannot fine-tune the existing object detection networks on the distorted images. This is where ObjectRL can be extended, where we have an RL agent which initially captures images by choosing random combinations of camera parameters. This will be the exploration phase. Then a human could give rewards according to the objects detected in the images in the current buffer. These rewards will be used to update the policy to improve the choice of camera parameters. This method of assigning a binary reward is comparatively much faster than annotating objects with bounding boxes. This methodology is quite similar to the dagger method by Ross et al., where a human labels the actions in the newly acquired data before adding it to the experience buffer for imitation learning. We define the metric we have used to evaluate ObjectRL in this slide. To the best of our knowledge, we believe no suitable measure is defined for this problem, and hence we define a measure called TP score of K, or the true positive score. TP score of K is the number of images in an image set I in which K or more true positives were detected which were not detected in the image before the transformation. The TP score of K is initialized to 0 for a set of images. For example, let the number of true positives detected before the transformation be 3, and let the number of true positives detected after the transformation be 5. Then we have one image where 2 extra true positives were detected which were not detected in the input image. Thus, we increase TP score of 1 and TP score of 2 by 1. To obtain the baselines for comparison, we first distort the images in the original data set, with alpha being randomly chosen from the set 0.1 to 2 or 0.5 to 1.8 depending on the distortion scale. The set of available actions to be applied on these distorted images for obtaining the baselines is the reciprocal of all the values in the distortion set. We evaluate the TP score on the distorted images by applying the transformation, by performing a grid search over all the values of alpha in the action set, and report the scores obtained with the best performing action for different types and scales of distortion. So these are the learning curves for agent for brightness, color, and contrast. Here the rewards are plotted with the moving average of window size equal to 30, and each iteration in the plot represents 1000 episodes. Here we show some of the outputs of ObjectRL. The first row is the input image, the second row is the distorted image, and the third row is the agent obtained image. If you notice in the first column, we have 4 objects detected in the input image, 3 objects detected in the distorted image, and again we have 4 objects detected in the agent obtained image. Similarly, in the third column, we have 1 person detected in the input image, 1 person detected in the distorted image, and 2 persons detected in the agent obtained image. So the input image and the agent obtained image may not look pleasing to a human eye, whereas the distorted image is quite pleasing. But clearly this image is the optimal one for detecting objects and not these two. Similarly, we have a few more results. Here the class of the object changes from sofa to chair and again back to sofa. Similarly, here we have this group of people not being detected in the original image and them being detected in the distorted image as well as the agent obtained image. So here we show the table with the TP scores for brightness distortion on both the distortion scales with SSD and YOLO V3 as detectors. Here we can see that ObjectRL does not work well as grid search for full scale distortion, but it works as well as grid search in minor scale distortion. Similarly, these are the results for color. Again, we have similar performance with grid search for ObjectRL in minor scale and not as good as grid search in the full scale distortion. And similarly for contrast. Moving on to the next slide, we have cross policies. Here we perform an experiment to check for the dependence of ObjectRL agent on the object detector. So we use the policy trained with the rewards obtained from the YOLO detector with SSD and vice versa. We report the number of images where K or lesser true positives were detected with the swap policy than what were detected using the original policy on their corresponding detectors. Here we can see that pi SSD on YOLO is worse than pi YOLO on SSD. Note that higher this number, the worse it is. This difference in the performance is because of the range of values for which SSD gives optimal performance is bigger than the range of values for which YOLO gives optimal performance. In essence, YOLO is more sensitive to the image parameters than SSD. Future work includes combining all the distortions together instead of one at a time. Also, local manipulations can be made in the images. For example, the brightness can be changed only in certain regions of the image. And finally, extend ObjectRL for choosing camera parameters in real time. I would like to thank Hannes Goniajic, Rahul Ramesh, and Manan Tomar for their insights on the project. And thanks a lot for watching.